Nature's most interesting puzzle. Welcome to Miss V's math class. Today I'm going to show you some ways to solve systems of equations. If you haven't already done so, please watch the writing systems of equations video, which is the precursor to this one. Before diving into today's subject, there's a couple things that I want to quickly review. When it comes to systems, what is a solution? It's a point or points that lie on both or all of the functions. This point or points will satisfy both or all of the equations. So how can we find these points? There are three methods we'll go through in this video. The first one is graphing. Now, there are some limitations to this method. Obviously, the availability of technology, and then most graphing calculators can only graph in 2 dimensions. Practicing on the same calculator that you will be using for the test. Now, if you're not sure if you're going to have a calculator on the ACT, or if you don't know which one, then it's best not to rely on this method. Different calculators can function differently, and you definitely don't want to spend test day wasting your time trying to figure out your calculator. In this video, we're going to use graphing as a way of checking our answers. I use a website called Desmos. It is free for the public and only requires an internet connection. The second method we'll go through is substitution and then elimination. These can be done by hand, so they're very useful for testing purposes. All right, first let's talk about substitution. This should be a familiar concept for you guys because we've done quite a few practice problems with substitution before. The idea of substitution is that we can replace a term with anything that is equal to it. Let's look at an example. I start with these two equations. Look at the second equation. Since x is equal to 4 minus 2y, I can replace any x's with 4 minus 2y and still maintain equality. I'm going to use that in the first equation. Watch what happens. Why is this helpful? Well, now we have gone from 2 equations with 2 variables to 1 equation with 1 variable. So this is easy to solve with inverse operations. Simplifying, I get y plus 4 is 2, which means y is negative 2. This is half my solution. To find the x value of the solution, I can simply substitute the y value into either of the equations. So my solution is x is 8 and y is negative 2. I can check my answer because both the numbers should fit into both equations. And sure enough, when I substitute those values, I get a statement which is true. The solution can also be communicated as the coordinate point 8, negative 2. If I were to graph the 2 lines, they should intersect at that point. Let's check using Desmos.
I dream I know deep of my feelings for you. Watch them grow, perceive devote. This is the seed, light the show. Watch them grow. Grow, grow.
Let's do a second example. This one comes from a past ACT. It asks, what is the value of y in the solution to the following system of equations? So here we only need to solve for y, not x. These equations aren't really set up to easily substitute the way that the first example was, but I can still use substitution. I just first need to solve one of the equations so that one of the variables is by itself. Remember how in the last example, after the first round of substitution, we boiled down 2 equations into one equation with just one variable? Well, this question asks for the y value, so that one equation with one variable should be in terms of y. That tells me I'm going to need to substitute for x to get rid of the x. So the first thing I'm going to do is get an equation of x equals something so that I can replace x with that something. Let's use the second equation. Notice how I've used parentheses around the value. This is important because if I didn't do that, I would not get to the right answer. Both of those terms inside the parentheses have to get multiplied by 2. I start simplifying by using the distributive property, multiplying by 2, and then simplifying, then using inverse operations until I solve for y. I've solved what the question wanted, but if I did want the full solution, including the x value, I could go back and solve for x, then check my answer. Another way to solve systems is through elimination. In my opinion, this is the easier of the two methods. However, once you start practicing, you can decide for yourself. With elimination, we add one entire equation to the other. So in this example, when we add the two equations, the negative 2y and 2y cancel each other out, leaving us with 2x equals 12. Once we have the x value, we can go back and use substitution to find the y value. Either equation will work, but I will use the second. So I'm replacing x with 6, and then I'm solving, and I get to y equals 4. So my solution is 6, 4, and we can check that using Desmos. Go back for a moment to the elimination step. There are two things I want you to notice. First of all, both of these equations were in standard form, so they lined up nicely for combining like terms. Secondly, see how the negative 2y and 2y cancel each other out. This is an important concept. Before adding the two equations together, we need to make sure that we have terms that will cancel. Otherwise, the process is useless. Look at this second example. Right now, if I added the two equations together the way that they are, nothing would cancel. However, if I manipulate the second equation by turning the x into 3x, then the x terms will cancel. I'll have 3x on top and negative 3x on the bottom. I can do this by manipulating both sides of that equation, multiplying them by 3. So when I multiply both sides by 3, I'm left with negative 3x plus 6y equals 60. Now I'm going to add the two equations together. The 3x and negative 3x cancel, and then from there I'm able to solve for y. I can use that value for y to find x. Again, I can use either of the equations to accomplish this. I'm going to choose the bottom equation just because it looks a little more simple.
This is the seed, light the show, watch them grow.
Which of the two strategies do you think would work best with this problem? I would vote for substitution because the second equation is set up already equal to y, so it would be easy to replace y in the top equation with x minus 15. Elimination would require several extra steps. It would still work, however, it would take longer. As you practice more and more, it'll become very apparent to you whether for each problem substitution or elimination is going to be faster and easier. It's really important to be able to determine which one to use because it can save you quite a bit of time as you're working through the ACT. In the 4 examples that we've done so far, all of them have resulted in one solution. Now hopefully from watching the prior video you know that not all systems will have one solution. Sometimes they're going to have more than one, sometimes they're not going to have any solutions. So let's take a look at some examples that address those scenarios. I'm going to graph these so that you can see what happens. As you can see, it turns out these two lines are actually the same line. So let's look at how we can prove that algebraically. I'm going to go ahead and solve for x in the first equation, in other words, get x by itself. Then I'm going to substitute that value into the second equation. So I'm replacing the x with 3 minus 5y, using distributive property, simplifying the 6 and negative 6 cancel each other, and I come to y equals y, a statement which is always true. So for any value of y, the two lines share that value. So in other words, all the points on the line are the same as all the points on the other line. That means there are infinite solutions. All right, let's look at another example. In this one, these are both in standard form, so I'm going to use elimination. As it is right now, no terms are opposites of each other, so nothing's going to cancel. So I'm going to pick to multiply the top equation by negative 2. Then that'll cancel my x's. So when I do that, I come to negative 4x minus 6y equals negative 24. I'm going to add that. And notice not only does the x term cancel, but also the y term, leaving me with 0 on the left side and negative 30 on the right side. Interesting, because 0 never equals negative 30. So that means the two lines are never equal. They don't intersect. In other words, they're parallel. All the examples we've looked at so far have been linear equations. However, systems of equations do not have to be linear. Take a look at the next example, which uses quadratic functions. Graphed on a coordinate plane, the system appears like this. The two parabolas intersect at 2 points, 1 and -1, therefore there are two solutions. We can also do this algebraically, setting them equal and solving. Just like lines, parabolas do not necessarily have a point of intersection. Look at the system below. If I set the equations equal and then solve, I come to x squared equals -1/6. Here we've reached a contradiction because a number squared is never negative. So in this case, there are no solutions. Now you've learned how to write systems and how to solve systems. On the ACT, you will more likely have to do both for a question. You'll be presented with a real-world situation, you'll have to write the equations, and then you'll have to solve the system. So it's very important to be able to practice both of these. In your practice problems, please work on getting very, very comfortable with solving systems algebraically. Then we can jump into the multi-step problems. I hope this helped. Get out there and practice hard.
Decimals,
Quadratic function.
linear,
Different.